It's my pleasure to welcome you all this evening to our second seminar for Digital Classicist Berlin, our second year running this seminar series. And I just would like to begin with a couple items of business before I introduce our speaker this evening. So in order to ensure that we have funding and demonstrate to the powers that be our sponsors that people are interested in our attending, we have a sign-up sheet that I believe is over here being passed around. So please do annotate your details there, and also your email address if you're not already on our list, so you can get further announcements about our program, which is posted on these leaflets here. So please feel free to take some and pass them around to colleagues or put them in your department. So there are many here on the table, so please take those away with you. Please have a seat. And let's see, I guess the other sort of main thing to let you know is, as we're sitting here in the kitchen in a very sort of casual, informal atmosphere, this is something that's fundamental to Digital Classicist, and this, what we're doing here in Berlin actually takes its inspiration from Digital Classicist in London, which has been running for several years there with King's College and the University of London. And the main aim of Digital Classicist is to provide an informal environment where we can all come and speak and discuss freely our research, and particularly research that's in progress, that's ongoing, is something that we try to focus on here, so that we can create this nice discussion, this nice forum with emerging and research sort of on the go. So to sort of facilitate that process, even though we're recording now, this is sort of the more formal side of the seminar. We'll divide the discussion at the end of the talk into two sort of phases, and we'll turn the camera off after a period, and then we'll crack open the wine and the nibbles so that we can continue the discussion in a more sort of informal way. So I think that covers sort of the main matters of business, and then it just remains for me to introduce Martina Trognitz, who's going to be speaking to us this evening on an expert system for Vases of the Antiquity. And this is research that derives from her master's dissertation in Heidelberg in computational linguistics. Okay, so over to you, Martina.
Thank you. So the title of my talk today is EVA, an expert system for Vases of the Antiquity. What is EVA? It is, as the title says, an expert system for computer-aided classification and dating of ceramics, and it represents an application of natural language processing methods for an archaeological problem. And this whole thing was part of my master thesis at the University of Heidelberg in the field of computational linguistics. So what you will hear today is I will talk a bit about the motivation behind why I got this topic. Then I will talk a bit about the problem of dating the ceramics, give you an introduction to expert systems, and then we will see how the system is implemented, and lastly we will finish with a discussion. So the motivation behind this program was that I was looking for a topic for my master thesis that combines archaeology and computational linguistics. And at some point at the very beginning of my studies, I heard about expert systems, and one day I came up with the idea that why not do an expert system for some archaeological topic. And as it is in archaeology, there's a huge amount of unclassified ceramics that are still somewhere in some cellars and boxes and hidden away. And there are not enough human experts to classify them. So why not fill this gap with an automatic system? And this program, EVA, could provide a second opinion, or may even be used as a learning tool for students to learn how to look at ceramics to come to a classification or some dating. So the problem is, ceramic is a common find in archaeologies and excavations, and the form and the decoration of the ceramics depend on various factors and change in the course of time. So they depend, for example, of the cultural environment, depend on the source where they were produced, depend on the taste and fashion of the people to that time, and also technical achievements may be seen in the changing of the forms and things used to make ceramics. And that's why ceramics are used to date archaeological find deposits. So ceramics serve as type fossils. As Tom Rasmussen and Nigel Spavey state quite good, as I think, is that an ancient Greek vase is a difficult object for the non-expert to come to terms with, faced with rows of apparently undifferentiated black, red, and buff pots. He or she is at a loss as to where to begin. So this is somehow a kind of problem, and the solution would be store the knowledge of a human expert into an expert system to classify and date ceramic. And this is what I want to do. But I think not everybody knows about expert systems. That's why I want to give an overview about expert systems. An expert system is a program capable of solving problems similarly as a human expert would do. And this program uses knowledge and inference methods to solve the problems, and thus it can also solve very complex problems that normally would require an enormous human expertise. And the man you see here on the right is Edward Feigenbaum, the so-called father of the expert systems, because he developed the first one. These class of programs are a subject of artificial intelligence, and the earliest systems were developed in the 60s, the first one being Dendral, developed by Feigenbaum. And Dendral is a program that analyzes mass spectra of organic molecules, so the topic of this program is chemistry. Since the 80s, expert systems are used commercially, and there is a wide range of subjects on which expert systems may be used. So, for example, you have Mycin, that is a program to identify bacteria and recommend antibiotics, so its field is medicine. Then there is Prospector, that is a geology program to analyze geological data for minerals. And then there's also XCon or R1 that is used to configure computer systems. And from looking at all these different programs, it's also clear that an expert system normally only works well in a well-defined special field that should also be quite narrow. As soon as you start to expand it to a whole bunch of topics, it's more difficult to program that program, and the results won't be as good as when you have a narrow field. In practical use, an expert system takes some facts and information from a user, processes these, and gives out the expertise to the user. And the expert system itself consists of a knowledge base where all the information about a topic is stored, and has an inference engine that says how the information should be processed. So it's like a bunch of rules that tells you what you have to do to get from a knowledge with a given fact to a new information. And the inference engine makes deductions with taking information from the knowledge base and taking facts from the user that are stored in the working memory. And by making these deductions, it may also be possible that new rules will have to be applied, and these ones are stored in the agenda. And so it turns around until it's finished and has an output. The properties of expert systems are that they are high performant, and the results of these programs compete with those of human experts. They have a proper response time, so you don't have to wait days to get a result. It's almost as fast as a human. They are quite robust, should be understandable, and if you program them so that you can get out the information and restore it with another, so that you can get out the knowledge base and restore it with new knowledge, then they are also quite flexible. And the most important thing is that the knowledge is explicitly disconnected from the processing part of the program. So the deduction part is disconnected from the knowledge part. And so normally you should be able to exchange knowledge. Yeah, then now I want to show you how I did it with ceramics. Before implementation, there were a few thoughts to be made. First one being the size of the knowledge domain. I had only half a year for the thesis, so the first title engine vases was reduced to proto-geometric and geometric vases, and then even more it was narrowed down to Attic geometric vases. Then I had to think about how the knowledge base should be made, and I came up with a sort of a rule-based system that is based on a decision tree. I will show it in a few minutes. And then it is also important that you know that the knowledge base is somehow dependent on the inference engine. This means that how I store the knowledge says how the knowledge will be processed. So I can't store knowledge like I can make it rule-based, then the inference engine should work with rule-based information. And the whole system is implemented with Python because I do some language processing, and that's the language to go with if you want to do language processing. So this is the system architecture. We've got the user who he has two options, either A or B. If he takes A, then he will get questions from the program, and he has to answer these questions. And these questions are used to traverse through the decision tree, so through the knowledge base and inference engine. And then with each question, the program gets more information and finally might get to a result. Or otherwise, the user may input a description text of a vase. That's the second choice, B. And these description text that describes a vase in natural language is processed, and the program automatically tries to filter the information to answer the questions from the description text given. So the knowledge base is the heart of the system, and in this knowledge base, a restricted, well-defined knowledge domain is mapped to it. And how the knowledge is represented depends on different things like the area of application, so the topic, then the scope, the source of the knowledge, and the functionality of the inference engine, as I stated earlier. And normally a knowledge engineer transfers the knowledge from an expert to the knowledge base of the expert system. But in this case, I was everything myself. So why did I come up with a decision tree as a knowledge base? It is so that you can describe a specific vase with a specific set of characteristics. For example, if you take an early geometric example and a middle geometric example, they're all the same. It's all, they both amphoras with handles on the neck, so neck-handled amphoras. And the only thing the only difference they have is that the motifs they are painted with are different. So the early geometric one has a band of slanting lines. So it's like these lines. And the later vase has a hatchet meander, a zigzag, and a dog tooth. So the motifs are more elaborate and more numerous. And so you can say if a specific set of characteristics is given, then you get a specific vase. And if you store this in some kind of tree, so let's say you ask the questions so you start with the figured question, and then you ask for the shape and so on. And if you all pull them up, you get like a path way down till you come to the solution. And you only refer in the path when the program asks you for the motifs. Then you have like one way goes to the early geometric one, and the other way goes to the middle geometric one. So this is how it would look like if you picture the decision tree. So the program starts up here, ask if the vase has figures on it, then you can say yes or no. Yes normally means late geometric. If not, then it asks for the shape of the vase, and then so it goes further down. And this decision tree is built in a module called tree pi. So pi is for Python. And each node in this tree consists of a value, a question related to the value, and a link to the parent node and a list of child nodes. So if you, the root node is special, but if you take a normal node here, you have the value that is no, and then you have the question related to this value, which is shape, and then you have a link to the parent node that is stored internally, and you have all the children listed in this node. This is important to know for traversing the tree. And the knowledge base, when you write it down, is stored in a text file, and the syntax is that you start with the root node, and then you go down all the questions. So in this example, we start with the root, and we ask if the vase has some figures on it, then you may answer yes or no. And then if you answer with no, you may ask for the shape. And in this part, you only can answer with amphora, but you could also write down like something like pixis and so on. And the questions, so you in this text file you also only write the short form of the questions. If you want to have the full questions, they are stored in a dictionary in a file called dictionary.py. Are there any questions so far? Okay. Then I'll continue with the description texts that concern this part of the system. Let's consider this vase and the description for it from the Corpus Vasori, from the C4A. And the information about the vase is encoded in the text. Well, it's also encoded in the image, but in this program, it's only looking at text. And somehow you have to get the information out of the text to answer the question, for example, has the vase figures on it? What shape has it? And so on. So the informational parts are stored in the sentences, and they also depend a little bit from one each other. For example, in this sentence on the belly are linked dots, it is important that you have linked dots and that they are painted on the belly and not on the shoulder or on the neck or otherwhere. Yep. But the problem with description text, so natural language text, is that the form and the structure of the text depend on personal style of the writer, on the language skills of the writer, and also of the knowledge of the subject. I think someone who has never came up with antique vases may describe it totally different from an expert. And there even might be, it may even be that some informations are completely missing, just because they didn't seem important or they didn't know about them. So, if we have the question, at which part of the body are the handles attached, there may be, these are only 4 possible answers, but there the answer to this question might be encoded in different sentences. Or, for example, we can say, this neck handle amphora has a thick barred rim, or we can say, this is a neck handle amphora with a thick barred rim. And the information can be extracted using information extraction, and for this we use patterns to look for specific things. So for the question, at which part of the body are the handles attached, we would use, for example, these 2 patterns where we look for a string and a dash and handled, so that would cover this one and this one. Or we could also look for handles somewhere in the text and then some verbal phrase with the word on or to. And then the string that should be a nomen. So for example, that would be the handles are on the neck. So we have here handles, then some verbal phrase which is are on the neck. And then this string would be matched with this one. So to process these texts in the program, they first parse with a Stanford parser, and then the program starts going through each question, takes the question, looks up what patterns are stored for this question to get out and then starts to do information extraction to get the answers out from the text for the questions. Yep. So, I will now show you how the program works and looks. Just as you know, the main module is called Core, and when I start the program, it first starts to build the decision tree from the given knowledge base with the module tree. And as I already said, the user-friendly questions and also answers and the patterns are all stored in dictionaries. Pi. So okay. This is the place where the program is stored. Here are the program files, and now I will start it. Okay, it starts with an welcome. Hello, I'm Eva, and so on. And it already has built its knowledge base, and it also asked me if it should show it. For this, we can enter yes to show the knowledge base, and then you can see that we've got a tree starting here with root asking Fidgat, and then the second node is yes or no. And then for yes, there's only one answer, and then for no, we have a bit more. It asks for a shape, and then there are different shapes, and so on. Okay, so now the next thing the program wants to know if we want to answer questions or to input a file with a description. I will start with the answer mode. And now we start with the first question, which is, has the vase figure decoration in it? And then it says, by figure this means humans, animals, and the like. And it also gives you the possible answers you can say. So for example, if we take the vase we have seen earlier with a snake on it, we can say, okay, it has some figure on it, so we say yes. And then the program is already finished because it says it's late geometric, and there are only a few exceptions that date to middle geometric 2, and even fewer that date earlier. So that would be one first result of the program. So now I start it again. This time I don't want to see the knowledge base. I could do another round with questions. So for example, if we now say there are no figures on it, it asks for the shape of the vase. And here the possible answers are amphora, oinochoa, rybalos, cup, hydria, cantharos, and so on. Anybody has a suggestion? Culex. Then we'll take culex, and now it says, this is what I think. Are you sure it is a culex? This shape was not used in geometric times.
What happens if I make a typo? What happens if I...
then you have entered the wrong answer. I can do it. And you would have to start again. So for example, if now instead of typing yes or no, I just type N, it says N is not a valid answer, and that the program can't tell you anything more. I could program in that it also asks again, but not today. So now for the description text. So now we enter D, because we want to enter description text. And now it asks me that if I already have a parsed text, I may call it, or I may start a new one, or input a new text and call the parser new one. And I will do this. So I call it parser. And now it wants to know where the location of the description is. And it also says that each sentence of the description has to be in each line, because otherwise I would also need some sentence splitter. And so now we take, wait a second. Let's take test. So this is in the same directory. Where are we now? Yeah, it started the parser now. It did its thing with the parser, and here it says it's done with parsing. And now it will proceed with the output from the parser, and now we'll check for the answers in the text. And so the first question is the question for figures on the vase, and it couldn't find any figures in the text, so it answers this one with no. And now the problem is that the program can't find what the shape of the vase is in the given text. And it couldn't find anything at all. So now I can help the program and tell it that we've got an amphora in this text. I'm not quite sure what is in the text. I think there is some stupid sentences in it. Yeah, and now for the next question, it doesn't find the answers as well. So again, we'll have to help it. I've said neck, and now the program says, oh, this is a neck-handled amphora. Because in this case, for neck-handled amphoras, the knowledge base isn't further described, stops at neck-handled amphoras. So now I just have to check for a better text. Because in test, what had we in there? Yeah, it was a test text to test the Stanford puzzle. That's why it didn't find anything. So now we'll take, let's try this one. Yeah. So now it starts again with the parser. We have to wait a few instants, and now it has something in it. And now it found that there are no figures on the vase and asked for the shape, and the shape is skyphos. And again, it says skyphoi are only used mostly in middle geometric 1 and middle geometric 2 times, so 850 to 760 before 0. Yeah, good. Do you want to see any further examples?
Do you have an example that is a little bit more extent?
We could try. I think not with description text. What we could do with answering. Yeah. I think the belly amphora are better. Okay, so we have no figures on this one, and we've got an amphora, and now the handles are attached to a belly, and it asks if there's a plastic ring below the lip, and let's say yes. Then it comes out that these kind of amphoras were produced from early geometric 2. Yeah. Otherwise, if you want to see how far the knowledge base is developed, then this one with the belly amphora and the plastic ring below the lip. Then for the pyxis, we also have the type, so it can be a globular pyxis, a flat or a pointed, and then in the globular pyxis, it already asks for the lip form. In the knowledge base, I didn't go further with all the figured parts, with the decorations and so on. I'll tell you in a few moments why. Okay, let's go back. So, as you may see, the program is in an experimental status. And there are a few drawbacks. First of all, it is very time-consuming to write down the knowledge base. So, because there is one book about geometric pottery from Coldstream, and you would have to read that through and try to put the things he states in each chapter for each time period. You have to try to put it into a knowledge base, but this book isn't enough. I tried, but there are so many things that are still somehow not written down. And that is the other problem with writing and writing down. The program is very abstract because it doesn't consider the image of the actual vase. So because there are some differences in the change of times that are only seen by looking at the vase. For example, in an amphora from early geometric to late geometric differs also that the later ones are a bit slimmer and somehow taller and straighter, but this is something you can't really write down so good. And that is what makes working with only text a bit difficult for this program. But in future work, there could be included some image recognition to work with. And I also think that, well, now it was all text-based, and the terminal and the interaction with the program was also only on textual basis. It would be quite good to make a graphical user interface, so that the program could also show some examples what is meant. For example, when it asks for the shape of a vase, it could also say, look, this is how an amphora looks like, and this is how a cantharus looks like. Well, then the knowledge base can still be further expanded. There could also be included more regions and earlier and later styles. Then it would be nice to have additional languages, so that you not only have to work in English, but could also, let's say, translate it in German or French or anything. And as I said, building the knowledge base is very time-consuming. It may be interesting to make that with the help of machine learning. Although for that you will need a very large corpus with descriptions of vases, and that is something that is missing somehow. We have the Beasley archive online, but that is for geometric times. It has only like 2 examples, and then from the CVA they have some things online, but it's all stored in PDF. And trying to work with PDF's text and extracting text is not funny. Yeah, and as I said, include image recognition. I think that would be the most feasible part, to try to classify vases with a whole bunch of images and cluster them. So what I think is that computer-aided classification and dating of ceramics is possible. Yeah, what do you think?